Okay, so let's start afternoon session. Okay, so the first speaker is Professor Antoine from Caltech. He's a winner of Frontiers of Science Award, and his title is Generic and Random Behavior of Minimal Surfaces. So let's welcome.
Thank you. Thanks a lot for the invitation. Thank you, Kotaro, for the introduction. So I'm going to talk about minimal surfaces, which is a kind of object that appeared in several talks already. But since I see some non-experts, I'm going to start a little bit slowly. I'm going to divide my talk mainly into two parts, which are technically very different, but which are actually about the same theme. So what is the main theme here? The main theme is about trying to understand typical properties of minimal surfaces. So minimal surfaces are this class of mysterious objects, and it's hard to say something about one minimal surface in particular, but maybe you can try to say something about typical minimal surfaces. And also I'm going to emphasize two connections between minimal surface theory with first analysis. I'm going to talk about the Weyl law or the eigenvalues of the Laplacians, and also with probability, in particular random permutations. So the relation with analysis is very old and I think studied by many, many people. And the connection with probability is much newer. The outline of the talk is I'm going to give you a survey of variational constructions of minimal surfaces. So how do you construct minimal surfaces? The second part is going to be the paper I have to talk to, which is this joint work with Fernando Cordal Marquez and Andre Neves. And it's in min-max theory. It has to do with the spatial distribution of the minimal surfaces that you can cook up, at least in generic ambient spaces. And the third part is going to be about the high probability behavior of minimal surfaces in spheres that you can construct from random permutations. All right, let's start with just the definition of a minimal surface. So these are a class of very well-studied surfaces in geometry. What's the definition? So let's consider a two-dimensional surface sigma immersed inside an ambient space M. So think of M as being, for example, the Euclidean n-sphere. That's going to be more or less enough. So we're going to say that this two-dimensional surface is a minimal surface if it locally minimizes the area. So what does it mean? It means that if you poke the surface somewhere, you're going to necessarily increase its area. So this is really like geodesics. Remember that a line in an ambient space is called a geodesic if locally, if you try to deform the curve a little bit, you're going to increase its length. So minimal surfaces are really a two-dimensional version of geodesics. And okay, they appear in many settings. They have many applications. One thing is that today I'm going to care about minimal surfaces for themselves. I won't care about any external application. On the contrary, I will care about what other fields have to say about minimal surface theory. Okay. So here's a slide to just tell you that there are many nice equivalent definitions for minimal surfaces. For example, one equivalent definition is to say that a surface is minimal if and only if its so-called mean curvature is zero everywhere. Another equivalent definition is that sigma is a critical point of the area functional. So think of sigma as being one element in the space of all possible surfaces in your manifold. Well, sigma is a minimal surface if it's a critical point of the area. Here's a more technical definition. A sigma is a minimal surface if and only if it's the image of a map which is both harmonic and conformal. So this is something very special. So if you fix a complex surface, a Riemann surface, and you map it into M by a harmonic map and which is also conformal, then the image is going to be a minimal surface. So you can think of minimal surfaces really as nonlinear analogs of harmonic functions. So this is something that's very nice, but also extremely nonlinear. And we're going to be interested in their interactions with, again, analysis and probability today. Okay, any questions? Within an isotopy class, so in full generality, there could be infinitely many, but if you look at more specific ambient spaces, say a hyperbolic manifold, and you try to ask how many minimal surface do you have in a homotopy class, I actually don't know the answer. I don't know if it has to be finite. Does it? Do you know, Daniel? Yeah, on the top of my head, I don't know. Yeah, that's a good question. What do you mean? An example where it's finite, this number? Oh, yeah, so for generic metrics, this is going to be definitely countable. Oh, so actually this definition holds in for any kind of surfaces, non-compact with boundary. But it's true that in this talk, I'm actually going to only care about sigma when sigma is a closed surface, meaning compact and without any boundary. So yeah, you should, as a picture, you should definitely imagine that we're constructing surfaces like this soap film, but we want to construct surfaces without boundaries. So in this real life minimal surface, there's a boundary here. In the constructions that we're going to do, we're going to have surfaces without boundary, and the ambient space is not going to be the usual Euclidean space, but some other ambient manifold. Again, so for simplicity today, we're only focusing on closed minimal surfaces inside closed Riemannian manifolds. And in general, so these objects are very difficult to construct. So if you look at the linear case of harmonic functions, it's kind of easy to construct harmonic functions. You solve the Dirichlet problem, you get a lot of harmonic functions. For minimal surfaces, it's a lot harder. And it's not even clear that they exist in abundance. So the very first question that appeared in the field is, oh, okay, do minimal surfaces actually even exist? Are they abundant? How do you construct them? And over the years, people developed several pretty general variational methods to construct minimal surfaces. In this talk, I'm going to mention two of them. So one is minimization methods, and the second is min-max theory. I'm going to ignore a bunch of other methods, in particular geometric measure theory, PDE methods, and special methods. For example, the lambda 1 minimization procedure that Daniel Stern talked about in his talk. So yeah, two methods, minimization and min-max. So for minimization techniques, Shen and Yao, Sachs-Uhlenbeck devised a minimization procedure to construct minimal surfaces in general Riemannian manifolds. And this construction is non-explicit, but here's the basic principle. The basic principle is that you fix a class of surfaces, say a homotopy class of surfaces, and you want them to a priori satisfy some constraints, maybe some topological constraints or some symmetry constraints. And among these surfaces, you're going to try to minimize the area. Think of it as minimizing the energy, and you get a minimizer. Remember that minimal surfaces are critical points of the area, so if you get a minimizer in particular, you get a minimal surface. That's the picture. And related to the previous question, so for instance, what can you do with this kind of theory? So if you have, this is very related to topology, if you have a pi1 injective surface somewhere in a Riemannian manifold, you can actually deform it to a minimal surface up to some caveats. Is there any question on this slide? All right, so this is the first method, just minimize, the most kind of obvious method. But sometimes minimization doesn't give you anything non-trivial. Minimization is only going to give you the empty set. So think of if you have a bunch of surfaces in a sphere and you try to minimize the area of this surface, then you can try to deform this whole surface around a point, and in the limit, everything disappears. So you haven't constructed anything. In the limit, you just get the empty set. Exactly. So in the end, in the last part of the talk, we're going to impose some symmetries, and then we're going to get something non-trivial. But let me first mention what you can do if you don't impose symmetries, but you do something else, which is called a min-max theory. So that's different from minimization methods. So minimization methods, you're trying to construct minimizers of the area, this landscape of surfaces. In min-max theory, you're going to try to construct higher index critical points. So not minimizers, but maybe other critical points. And I should say that Fernando Corral Marquez and Andre Neves really played a huge role in the development of this theory. And again, this construction is highly non-explicit. It's deterministic, but it's non-explicit. So the basic principle is that, again, since minimal surfaces are critical points of the area, you can try to construct them by using some mountain pass argument and try to find some critical points that are not minimizers, but saddle points. There are many applications of this theory. Let me mention one striking example, which is the Vilmore conjecture that was solved using this kind of techniques by Marquez Neves. There was a conjecture of Yao about the existence of infinitely many minimal surfaces in three manifold that was solved by this kind of theory. And more recently, there's been a breakthrough on the so-called four minimal sphere conjecture by Zhichaovan and Xingzhou. So this is the second set of methods to construct minimal surfaces. Questions on this slide? So to summarize, we have those general methods to construct closed minimal surfaces in closed Riemannian manifold. What can you do with them? First observation is that really there's a lot of them, actually, because of those theories. And so it's hopeless to try to classify minimal surfaces in general. And besides, the constructions that we described are very implicit because they're based on some compactness result. And so it's very hard to describe the resulting surfaces that you get. When I say describe, I mean, describing the curvature of this surface or describing the position. Where is the minimal surface? So it's more hopeful and fruitful to actually look at typical behaviors. And so the next question, which I think has guided a lot of the recent work in minimal surface theory, is the following one. So what do typical minimal surfaces look like? Where are they located? How curved are these objects? Things like this. So I'm going to talk about two kinds of results. The first kind of results is going to be the generic spatial distribution of minimal surfaces. So it's going to be about the location, the position of minimal surfaces generically. And the second part is going to be the asymptotic behavior of random minimal surfaces that you can cook up using random permutations. I'm going to ignore a lot of other directions that are related to this problem, this typical behavior problem. Okay, so let me start with this number one. Number one, so consider a closed Riemannian manifold of dimensions 3, say, and nowadays we know that there's a lot of minimal surfaces in this space, but where are they? Can you say that there's a minimal surface going through any open subset, for example? And this is still unknown, by the way. So answering this in general is pretty much unfeasible. But everything becomes more tractable when the metric is chosen generically. So here, what I mean by choosing the metric generically, remember that the metric is this tensor that gives you a metric on the manifold. I'm going to say that it belongs to a generic set if it belongs to a well-chosen countable intersection of open dense subsets in the set of all metrics. Is there a question on the definition of generic? So if you can prove that a good property holds for a set of metrics like this, then you basically prove that this good property holds for almost all metrics of that set. All right, so the first statement is the following. If you fix, again, a closed three-dimensional manifold, then for generic metric on M, there's a sequence of minimal surfaces that equidistributes on average. And what that means is that you give me any test function f, you look at, you can integrate this function on each surface. You can sum over the first j surfaces in this sequence, and then you can normalize by the area. So this is think of it as integrating on the surfaces. If you let the number of surfaces go to infinity, then the sequence is going to converge to the spatial average of your test function. Does it make sense? So you see that it's an equidistribution on average. Going to be maybe too lazy to draw a picture, but you should think of, you have this ambient space and you have so many minimal surfaces that you can choose them so that they kind of become uniformly distributed in the ambient space. And this is very quantitative because this really holds for any test function. And this quantifies a previous denseness result by Erie and Marquez-Neves that maybe I'm going to mention later. But for now, let me give you the almost opposite version of the previous theorem. Again, let M be a closed three-manifold. And for a generic metric, you can also say something like this. So if there exists an embedded stable minimal surface, whatever that means, then there is another sequence of minimal surfaces that does the opposite of being equidistributed. So what they do is they scar along S, so they tend to concentrate along S. And what that means is that you have this sequence of closed surfaces with area growing to infinity. And moreover, if you normalize these surfaces by their areas, these, as they measures, they're going to converge to the normalized surface S. Remember that S here is just a two-dimensional surface. So that means that all those surfaces are going to, on average, concentrate along a lower dimensional manifold. So it's the opposite of equidistribution. So what's surprising here is that you have two completely opposite behaviors, but happening more or less at the same time for generic metric. For generic metrics, you can have both kinds of sequences. But let me give you some intuition here. The intuition is that most surfaces should behave like equidistributed surfaces. And you should think of those kind of surfaces concentrating along submanifolds as being sparse, very sparse in the space of all minimal surfaces that we care about. Let me see if there's a question on the statements. That's right. That's right. Yeah, so I think it's time to take out a chart and actually do some drawing. So you have to imagine that maybe your ambient manifold looks like this, and then this is some spectral surface S that I'm claiming often exists. And then you have to imagine that the surfaces sigma k here, they have a lot of oscillation, as you said, but on average, maybe they do this sometimes, but most often they're going to stay around S. So the two-dimensional picture is that if this is S, then the approximating surfaces is going to look like, maybe a lot of sheets that are connected by some small necks. So you see that those surfaces, they have a lot of sheets, so they have huge area, but they stay kind of close to a flat surface.
How did you use the stable?
That's kind of hard to explain. It's a little bit technical. I don't know, for example, that's a good question. I don't know if such a theorem would hold if you take just S any submanifold, any minimal submanifold. Right.
Yeah.
So I'm not claiming that this is optimal at all, but this is what, yeah, in our theorem, the proof we need stable. No, that's the interesting thing. Just because of the maximum principle, actually, this picture is misleading, but this neighborhood is mean convex. It's kind of convex. And so any minimal surface that's completely contained here, you can show that it has to be equal to this S. But somehow the sigma k that we construct here, they actually go outside. There's no contradiction here. So we have those two completely opposite behaviors, and I'm claiming that for clarification, that this should be the real generic or typical behavior. That should be very degenerate. And I don't know how to prove this, but let me move on to some analogy, which I think should be helpful. So one of the motivations of min-max theory is that there's this very strong analogy between min-max theory and the usual spectral theory for the Laplacian on the manifold. So remember that the standard theory for the Laplacian is that you give me a closed Riemannian manifold. You have the Laplacian operator, of course, acting on functions. It's diagonalizable, and you have eigenfunctions, and you have eigenvalues. You have a sequence of numbers going to infinity, which are the eigenvalues of the Laplacian. And you can argue that those eigenfunctions, you can think of them as critical points of the so-called Rayleigh functional. This is very classical. And another thing that's classical is that those numbers, you can express them as min-max quantities, like that. Right. So this is the classical theory about eigenfunctions and eigenvalues. And another thing about which is nice about those eigenfunctions is that we can control the rate of growth of those numbers. This is called the Weil law. The Weil law is going to say something like this. So let n of lambda be the number just of eigenvalues enter this number lambda. This is a finite number. And the classical Weil law is telling you that this number grows as a power of lambda, at least on the three manifold is this power. Yeah. So on an n-dimensional manifold is this power, and it depends on the volume, okay? And there's a more powerful, but also extremely old theorem due to, I think, Avakumovic, which is the pointwise Weil law, which is stronger. It's telling you that if you normalize each eigenfunctions so that the L2 norm is 1, then you can consider the following function. So now it's not a number, it's a function that depends on lambda and x, which is what? You take the sum over all the eigenvalues that are less than lambda of this L2 energy. And the pointwise Weil law is telling you that this function is pointwise expanded like that. So that recovers the traditional Weil law just because if you integrate this function, you get this number, right? So let me just say that what this means is that the sequence of eigenfunctions equidistributes on average. This is exactly what it means if you think about that. So eigenfunctions tend to be equally distributed in space. And also there are some results about sparse sequences of eigenfunctions that do not equidistribute, and this phenomenon is called scattering in literature. So that's classical Laplacian theory. No, so because I'm not claiming that a single eigenfunction is equidistributed. I'm taking the sum from the first eigenfunction to the lambda's eigenfunction. And in that case, every time you have this. But you're right that there's something called unique quantum ergodicity conjecture that tells you that in negative curvature, you should be able to get rid of the sum and just take phi p. That's a good question. For minimal surfaces, you mean? No, this is an open question. It's probably true too, but we have no idea. Questions on the Laplacian? So I'm talking about that because there's this very tight analogy between Laplacian and what min-max theory can do for you. And let me go through this analogy quickly. So again, strong analogy between min-max theory for minimal surfaces and spectral theory. So you're going to replace functions by two-dimensional surfaces. You're going to replace Rayleigh energy by the area, eigenvalues by some numbers called min-max widths, and eigenfunctions by minimal surfaces. So if you believe that there's this analogy that everything works, then what you have in the end is, for example, you have a three manifold and you have a sequence of numbers that are called min-max widths that converge to infinity again. This is, did I say? Yeah, it's an observation due to Gromov that there's at least, he was the first to try to emphasize this analogy. And then each, in the same way that eigenvalues are realized by eigenfunctions, those numbers are realized by minimal surfaces. And you also have a Weyl law, which is that those numbers, they grow in a controlled fashion depending on the volume. Okay, so I'm not going to give the proof because of the theorems, but let me say that given this analogy, the generic equidistribution that I mentioned before is very closely analogous to, the pointwise Weyl law of Abakumovich. Okay. Yes. That's an excellent question, and the answer is I don't know. I think so. It's one of the open questions that I wanted to mention. So on the other hand, the generic scattering result is more like those scattering result for eigenfunctions of the Laplacian. But I have to say that for the Laplacian and minimal surfaces, of course, technically, the proofs are just completely different. And this is the comment that you just made, which is that this analogy is far from being perfect because in Abakumovich results, it's a natural sequence of functions. You're just taking the first eigenfunctions that you have in your sequence. Whereas in our result here, we just get one sequence. And so moreover, in Abakumovich result, you have this result all the time. You don't need the space to be a little bit generic. Right. So for minimal surfaces, the sequence that equidistribute, we have to pick it very carefully. Otherwise, we don't know how to do it. And the question is, does the natural sequence of minimal surfaces that appear in min-max theory actually equidistribute on average? Probably yes, but we don't know how to do this. Is that question clear? All right, so let me say one word about the proof, which is that the proof of the generic scattering and generic equidistribution really is based on this Weyl law. And this is all I want to say about the proof, actually. So let's skip that. Oh, one important comment is that one of the ideas, key ideas, actually is an idea of K. Irié. So K. Irié is, he gave a talk, by the way, but he works in contact geometry and he's interested in constructing Rib orbits. And it turns out that there's an idea that he used there that's useful in our setting for minimal surfaces instead of Rib orbits. Move on to the other little half of the talk, which is about random minimal surfaces, and this is more recent. So let's consider the following question. What is the shape of a random pair of permutations as n goes to infinity? So how do you even make sense of this question? Well, we're going to make sense of that question using minimal surfaces in spheres. We're going to see that there's a natural way to associate to a pair of permutations a certain minimal surface. So if you give me one permutation and you choose it at random, there are many things you can say about this permutation. It's very easy. I mean, it's very classical. You can do some statistics about the number of cycles of this random permutation. But when you have two random permutations, then you have interaction between those two permutations. And it's very hard to actually describe what happens when you take random permutations. What does it mean for two permutations to be very random and very independent? So there's actually a whole theory behind this kind of question called free probability, also random matrix theory. We're going to see a geometric manifestation of the fact that if you take two random matrices, two random permutations that tend to be extremely non-commutative. Okay, let me fix a pair of permutations, sigma 1 and sigma 2. I'm going to quickly explain why they determine a group of symmetries of some sphere. Actually, it's very simple. It's a very natural thing. Remember that you can think of permutations as linear isometries, right? Just by permuting the coordinates. So if you give me two permutations, they're going to generate a finite group of linear isometries of the vector space on which it acts. Okay, sure. And moreover, the diagonal is going to be left invariant by all those by sigma 1 and sigma 2, because if you permute only once, it's going to be the same vector. So you can restrict yourself to the orthogonal. All I'm saying here is that what you get from two permutations is a finite group of linear isometries of some round sphere. Is everyone on board on this thing? So two permutations gives you naturally a group of isometries, a finite group of isometries of some round sphere. And so now the idea is you fix those symmetries. We're going to look at surfaces that satisfy this symmetry. We're going to minimize the area. You get a minimal surface. So this minimal surface is going to have this group as a group of symmetry. And we're going to be interested in what happens if you choose this group randomly. So if you choose those permutations randomly, what happens to the corresponding minimal surfaces? So is there any question on what's happening here? So it's acting on this sphere, right? S2n minus. Yeah. That's right. That's right. Actually, so that's right. Yeah, it's exactly right. So with high probability, this is just the symmetrical. Yeah. Oh no. Yeah, this is for maybe more geometrically minded people. So yeah, I didn't want to mention this fact. Okay. So once you have two permutations, you have a group of symmetries of some ground sphere. And recall that by this classical minimization method of Chen and Yao Saxon-Lundbeck, you can look at all the surfaces with these symmetries and minimize the area among all the surfaces. You get a minimal surface. And up to some caveats, again, this is true. And in our case, that means that given two permutations, you get a minimal surface that I'm going to call sigma n. Okay, a closed surface in a sphere. I'm calling this procedure the spherical plateau problem because I think it deserves a name because it has a lot of very nice properties and it works in great generality. Anyway, so two permutations gives you a minimal surface. And we interpret this minimal surface as the shape of this pair of permutations, sigma 1, sigma 2. In general, nothing exciting can be said about those minimal surfaces. And by the way, those surfaces could have been constructed in the 80s. The construction is completely classical. But the problem is that in general, you can't say anything very much interesting about those minimal surfaces. However, for random choices of permutations, suddenly something interesting happens. And the theorem is the following. So first, if you fix me a large, choose the permutations independently, randomly, uniformly, then with high probability, the area of this minimal surface, after you renormalize by the symmetry group, the number of symmetries that this surface is invariant by, this renormalized area converges to pi over 4. It's a very specific number. And moreover, you can say something about the curvature of your surface. So those surfaces are almost hyperbolic in the following sense. So the average of this function is very small. So that means that, so here, K is the Gaussian curvature of the surface, which is this classical notion of, sectional curvature, Gaussian curvature, whatever you want to call it. So that means that K is trying very hard to be constant equal to -8, right? So this surface is, in that sense, almost a hyperbolic surface. I invite you to try to imagine such a surface, because if you are a minimal surface with almost constant negative Gaussian curvature, the surface is trying to expand very hard, but we're constructing closed minimal surfaces, so compact minimal surfaces. Somehow, those surfaces satisfy some almost contradictory properties. Right, so I'm going to end soon, but let me mention that this is related to an open question in the field, which is due to Yao, which is there any closed minimal surface in any Euclidean sphere which has negative Gaussian curvature? So this does not answer the question, but almost, right? Because that means that the surface at most point is going to have negative Gaussian curvature. Any questions on the statement? No, so you should think of those surfaces as having genus and area going to infinity. And the genus, you can say something about its, how it grows in terms of this number, yeah. More or less just by Gauss-Bonnet. So that's the answer, right? That in general, I do not know how it depends on sigma 1, sigma 2. Oh yeah. So I didn't, describe the construction, but I told you vaguely that by Shen Yao and Sachs-Uhlenbeck, whenever you give me two permutations, I can get a minimal surface in a sphere. Because the permutations are going to define a group of isometries of the sphere, and your minimal surfaces is going to be invariant by those same symmetries. The minimal area one. All right, so yeah, so let me mention that one motivation, there was this open problem motivation, that is there are negatively curved minimal surface in spheres, which is interesting. But I think more interestingly is you have this motivation, this conjectural picture, which is typical minimal surfaces, they have to be mostly negatively curved. I think compared to the examples that we have in the literature, this is not obvious. This is not something that very much direct, because the examples that we get are typically, they have a lot of positive curvature. But let me compare this conjectural picture to other insights that you have and that are important heuristics in other fields. So for example, in topology, the heuristic is that most manifolds are negatively curved. In the field of group theory, geometric group theory, same insight happens. Most groups are negatively curved. In complex geometry, if you look at projective submanifolds, you have something similar. So what I'm saying is that this heuristic should also hold for minimal surface. Right, so let me give you the key probability result. Just the name is due to Bordenave and Collins. And it's a result about random permutations, which is very general. I just quickly mentioned that there's a new proof by Qifang Chen, Garza Vargas, Trop, and Ramon van Hendel. So let me end this talk by saying that we saw that in generic Riemannian manifolds, there's a sequence of minimal surfaces which equidistribute on average or scar on the contrary, and this is based on connection with the Weyl laws. On the other hand, we also saw that minimal surfaces in spheres representing pairs of random permutations, they have a very nice asymptotic behavior. They basically converge to the hyperbolic plane. This is the unique possible behavior with high probability. And there are two conjectural pictures. The first, natural sequences of minimal surfaces, they tend to be equidistributed. Any result in that direction would be fantastic. And the second picture is that minimal surfaces tend to be mostly negatively curved. And this is related to the random picture, the random result that I mentioned. So thank you for your attention. And let's see if there's any questions.
Thank you very much for the great talk. Okay, are there any questions or comments?
In your first theorem about the approximation of general manifold by minimal surface, you use a test function in some sense. Will it be more difficult if we do double integral or triple integral?
Oh.
Because in some viewpoint, this is like a linear statistic.
Good question. I have no idea. Yeah, I have no idea. I have never thought about this question, but makes sense. Yeah, so conjecturally, the result should generalize to any number of permutation that would correspond to some other surfaces, but they should, with high probability, again, be close to being hyperbolic. There are some difficulties in the proof, so I don't know how to extend it to more permutations. So I stated for two only. No, so that's what's interesting, right? So I don't know how to prove it's not unique, but definitely you don't expect the minimizer to be unique. However, in the limit, it's unique. So this is some kind of asymptotic rigidity that I find new and funny. Right. So for example, you can think of the unitary transformations as also being transformations on CPN, right? And you can maybe try the same thing I've never tried. But this is a problem that makes a lot of sense. And you can ask the same kind of question, but for other symmetric spaces, you have a bunch of transformations. Maybe you take them randomly. Maybe the corresponding surfaces have very nice limiting behavior. It might be different, indeed. Yeah, so that's a tough question. So because on the nose, there's no eigenvalue problem here. But I should mention, and this is connected to Daniel Stern's talk, which is that there are some separate constructions of minimal surfaces in spheres that are coming from studying the first eigenvalue, λ1 of the surface. Some extremal metric for λ1 gives you a minimal surface in some sphere of the classical Laplacian of the surface. So if you try to optimize the λ1 for on a given surface, it gives you a minimal surface in a sphere. And so maybe those two constructions actually are the same. So maybe the surfaces that you can construct using λ1 optimization are the same as those kind of minimal surfaces. And there would be at least in principle connection between λ1 and those surfaces.
Any other questions or comments? Yes, sir.
Right, so again, no, I don't think so. I cannot prove it to you, but there's no reason to think that there's a unique minimal surface that realizes it. But again, as I was telling Yongsheng, in the limit, the minimal surface is.
Any other questions? Okay, so if not, let's thank the speaker again.
Thank you.